So Cayley-Hamilton theorem. The statement of Cayley-Hamilton theorem is every square matrix satisfies its own characteristic equation. So we have to prove that every square matrix satisfies its own characteristic equation. So for this, I am considering an n by n square matrix. So let capital A is an n by n square matrix. Okay. So immediately after considering square matrix, I am writing the characteristic polynomial of capital A. And we all know that the formula for characteristic polynomial of capital A is det of A minus lambda I. And that is a polynomial of degree n, because we are considering an n by n square matrix so that we get nth degree polynomial. For example, if we consider 2 by 2 matrix, we get a quadratic equation in terms of lambda. Similarly, if we consider a 3 by 3 matrix, we get a cubic equation in terms of lambda. In the same way, I consider n by n matrix so that whenever I consider characteristic polynomial, definitely I get a nth degree polynomial in terms of lambda. Okay, so I'm writing the characteristic polynomial of A as det of A minus lambda is equal to minus 1 whole power n into lambda power n plus p1, lambda power n minus 1 plus p2, lambda power n minus 2 plus and so on plus pn, right? And in matrices, we are having one very, very important result, that is A into adjoint A is equal to det A into I. This is the result we are having in matrices. And in this result, I am writing A minus lambda I in place of A. Okay, I am writing A minus lambda I in place of A in the above result, so that we get A minus lambda I into adjoint of A minus lambda I is equal to det of A minus lambda I into I. I am treating this as equation 1. So we get this equation by replacing A minus lambda I in place of A in the above result. Okay, so now I am finding adjoint of A minus lambda I. So since A is a matrix, A minus lambda is also a matrix. And if we find adjoint of A minus lambda, that is also a matrix. And I am writing that matrix as B naught lambda power n minus 1 plus B1 lambda power n minus 2 plus B2 lambda power n minus 3 and so on, Bn minus 2 lambda plus Bn minus 1. So I am considering adjoint of A minus lambda I as in this way. Okay, so substitute this value in equation 1. So we get A minus lambda I into adjoint of A minus lambda I is nothing but, just now we consider adjoint of A minus lambda as B naught lambda power n minus 1 plus B1 lambda power n minus 2 plus B2 lambda power n minus 3 plus and so on plus Bn minus 2 lambda plus Bn minus 1. So I am writing the value of adjoint of A minus lambda I by from the above one, okay, is equal to, and in equation 1 we are having det of A minus lambda I on RHS. From equation 1 we are having on RHS det of A minus lambda I, and that the value of det of A minus lambda I also we are having in the above, so that we get minus 1 whole power n into lambda power n plus p1 lambda power n minus 1 plus p2 lambda power n minus 2 and so on plus pn. That is what we are having det of A minus lambda I into I. So I have written I as usual. Okay, so immediately after writing all the values in equation 1, now we have to compare the coefficients of lambda power n, lambda power n minus 1, lambda power n minus 2 and so on up to constant terms. So on both sides we have to consider all these coefficients on both sides. Now first I am considering lambda power n coefficient. Okay, so on LHS, if you multiply A with any term in the second bracket, we cannot get lambda power n term. Okay, because here lambda power n minus 1 is the starting term. After that we get lambda power n minus 2, lambda power n minus 3 and so on. So we cannot get lambda power n coefficient when we multiply with the A. Okay, and if you multiply with the lambda I with lambda power n minus 1, so if you multiply lambda with lambda power n minus 1, then we get the coefficient of lambda power n. Okay, so that I am writing as the coefficient of lambda power n as minus B naught I. Okay, if we multiply these two terms, minus lambda I into b naught into lambda power n minus 1, then we get lambda power n, and the coefficient of lambda power n is minus b naught I. That is the only term on LHS. Okay, if you multiply lambda I with any term, any other term in the second bracket, we cannot get lambda power n coefficient. And on RHS, the coefficient of lambda power n is minus 1 whole power n into I. So that is what I have written here, minus 1 whole power n into I. So the first equation is nothing but the coefficient of lambda power n on both the sides. Okay, so after that, now we have to consider the coefficient of lambda power n minus 1. Okay, right. Coming to the LHS, if you multiply a with the first term, so the first term in the first bracket with the first term in the second bracket, if you multiply those two first terms, we get the coefficient of lambda power n minus 1, and the coefficient of lambda power n minus 1 is nothing but ab naught, so that I have written ab naught. Okay, after that, the second term in the first bracket with the second term in the second bracket, second term in the first bracket with second term in the second bracket gives lambda power n minus 1 term. Okay, and the coefficient of lambda power n minus 1 is minus b1i, so that I have written minus b1i. So these are the only two terms we get when we multiply these two brackets on LHS. Okay, and on RHS, the coefficient of lambda power n minus 1 is nothing but minus 1 whole power n into p1i. So that is what I have written here on RHS. Similarly, if we consider the coefficient of lambda power n minus 2 on LHS, we get ab1 minus p2i, and on RHS we get minus 1 whole power n into p2i. I am considering the coefficient of lambda power n minus 2. Okay, and finally, and so on, and finally I consider the coefficient of constant term. I compare the constant terms on both sides. Constant term means yeah, and in the term it should not contain any lambda. Okay, right, and the constant term is on LHS is a into bn minus 1. Yes, when we multiply a with last term in the second bracket, we get the constant term, that is a into bn minus 1, and we are not having any other term other than a into bn minus 1 on LHS. Similarly, on RHS, the constant term is nothing but minus 1 whole power n into pni. So that is the constant term on RHS. Okay, so I consider all the coefficients of lambda power n minus 1, lambda power n minus 2, and so on, constant term on both the sides. Okay, right. So after considering the coefficients, now we have to pre-multiply the above equations with a power n minus 1, a power n minus 2, and so on I respectively. It means we have to multiply the first equation on left side with a power n. Okay, and the second equation with a power n minus 1, and the third equation with a power n minus 2, and the last equation with I respectively, and add all the above equations. So immediately after multiplying all the equations, we have to add all the above equations. So first I am multiplying with a power n. Okay, so we are having minus b naught I. If you multiply with a power n, we get a power n into b naught into I. Of course, b naught into I is nothing but b naught. Okay, is equal to. Similarly, in RHS also we get minus 1 whole power n into I into a power n. I into a power n is nothing but a power n, so that we get a power n. Okay, and similarly, if you multiply the second equation with a power n minus 1, second equation with a power n minus 1, we get a into a power n minus 1 is nothing but a power n. Okay, a power n into b naught minus a power n minus 1 into b1 into I is nothing but p1 is equal to minus 1 whole power n into p1 into a power n minus 1. So I am removing all the i's, because if you multiply any matrix with identity matrix, we get the matrix itself. So that I am removing all the identity matrices. Similarly, if you multiply the third equation with a power n minus 2, we get a power n minus 1 into b1 minus a power n minus 2 into b2 is equal to minus 1 whole to the power of n into p2 into a to the power of n minus 2. And finally, the last equation with identity matrix, we get itself a into bn minus 1 is equal to minus 1 whole power into pn9. Okay, right. So if we add now, next after multiplying all these equations with these terms, now we have to add all these equations. So now I am adding all the equations as I am adding LHS on one side and RHS on one side. So if you observe on LHS, So we get the first term minus a power n into b naught and a power n into b naught gets cancelled. Similarly, minus a power n minus 1 into b1 plus a power n minus 1 into b1 gets cancelled. In the same way, minus a power n minus 2 into b2 plus a power n minus 2 into b2 gets cancelled. And finally, we get a power a into bn minus 1 and in the above equation, we get minus a into bn minus 1. Those two also gets cancelled. It means on LHS, each and every term gets cancelled so that we get 0. And on RHS, in every term we are having minus 1 whole to the power of n. So if we take minus 1 whole to the power of n common, we get a power n plus p1, a power n minus 1 plus p2, a to the power of n minus 1, so on, pn9. Okay, and if we consider this minus 1 whole power n to RHS, we get 0 itself, so that we get a power n plus p1, a power n minus 1 plus p2, a to the power of n minus 2, and so on, pni is equal to 0. So this is nothing but the characteristic polynomial. Whenever if you write is equal to 0, we say that is a characteristic equation, and this characteristic equation is satisfied by A. Okay, that is what we have to say in Cayley-Hamilton theorem. Every square matrix satisfies its own characteristic equation. Yes, in the above characteristic polynomial, we are having the polynomial in terms of lambda. Now we are getting A in place of lambda, so that we conclude that every square matrix satisfies its characteristic equation. This is the theorem. Okay, right. And one result we are having that if lambda is an eigenvalue of a non-singular matrix capital A, then the eigenvalues of A inverse are nothing but their reciprocals. Suppose if you are having 2 is an eigenvalue of lambda of a matrix A, then what is the eigenvalue of A inverse is nothing but 1 by 2. So just reciprocal of the given eigenvalue. Okay, now that is the result we have to prove here, right? So coming to the proof, I am considering that x is the eigenvector corresponding to the eigenvalue lambda. So whenever we are having an eigenvector corresponding to the eigenvalue lambda, we can write by definition a minus lambda into x is equal to 0. This is the definition of characteristic equation. Okay, if we multiply these two terms, we get ax minus lambda into x is equal to 0. This implies ax minus lambda into x is nothing but lambda x is equal to 0. This implies this can be written as ax is equal to lambda x. So this equation occurs because of x is the eigenvector corresponding to the eigenvalue lambda. Okay, for square matrix capital A. Right. Now I am considering, I am taking this A to RHS. So this A, when you took it to RHS, it becomes A inverse. Okay, so that I have written x is equal to A inverse into lambda x. Okay, so and now that lambda on RHS can be taken into LHS. So that becomes 1 by lambda into x is equal to A inverse into x. If you write it neatly, we get A inverse into x is equal to 1 by lambda into x. This is of the form Ax is equal to lambda x. From the equation Ax is equal to lambda x, we say that lambda is an eigenvalue of A. In the same way, A inverse into x is equal to 1 by lambda into x. We say that 1 by lambda is the eigenvalue of A inverse. Yes, if lambda is an eigenvalue of A, then 1 by lambda is the eigenvalue of A inverse. It means the eigenvalues of A inverse are the reciprocals of the eigenvalues of A. This is the conclusion of the above result. Okay, right. Thank you.